Hi there, welcome to our today's lesson, science lesson. Our topic for the day being solids, liquids and gases. From our previous lesson, we were looking at how particles in gases, liquids move and those in solid vibrate in their fixed positions. In a general, a theory called kinetic theory of matter. In our today's lesson, we want to look at how some of these states interact with each other, the behavior they exhibit, and the observations you will make out of the behavior they are giving out. To start with, I want us to look at a relationship between a liquid state and a gaseous, a liquid state and a solid state. Interaction between liquid state and a solid state. When these two states come together, it leads to formation of what we call a solution, whereby solids will give what we call a solute. It gives a solute, and the liquids give what you call a solvent. Now, these two coming together, that is a solute and a solvent, will give us what we call a solution. Now, I want us to understand how a solute, a solvent, comes together to form a solution in terms of the kinetic theory of matter as we have been learning in our previous lesson. How that movement we learned in the kinetic theory of matter comes in to be of help to form a solution. And thereafter, we also look at this solution in different situations. You remember that in any situation in your house, for example, when you are preparing your coffee or tea, you will be adding in sugar in that coffee of yours, depending on the taste you like. So there's one who will use maybe 1 teaspoon, another one 2 teaspoons, and so on, up to a certain limit. So we shall also look at the different states of a solution. But for now, let's see how a solution is made. We learned that solids do not move. The particles in a solid state vibrate in a fixed position. We also learned that particles in a liquid state, they move, but they don't move as much as particles in a gaseous state. And in their movement, they move in such a manner that we call rolling. So particles in a liquid state roll over each other. When something is rolling, it means it is looking for stability. It means it is readjusting itself so that it can reach a more stable position or a state. So when you have a solute, which is a solid, being put into a solvent, which is a liquid, the liquid particles, which is the solvent, roll over each other to accommodate the solid particles that are not able to move. As a result, the solid particles will enter and fill into the spaces that are existing between the liquid particles. Let's use a model maybe to understand much better on how these solid particles enter into the spaces of the liquid, which is the solvent. If you can have this as a container, maybe a glass of water or any solvent for that matter, and we use the black balls as particles of a liquid we said that they are close together but not as close as the ones in solid state, but they are a bit close. Now those are the particles of a liquid, what we are also calling as a solvent. Let's use the red to show particles of a solid. Remember, movement or rolling is to the particles of a solvent, not the solute. The solute is only forced to roll over to those positions by the rolling molecules or particles of a solvent. So when they roll, they enter into the spaces left by the solvent molecules. When doing this, then we say the solute is in the process of dissolving in the solvent to form a solution. However, at this state, the solubility process is not yet over. It is just one of the steps. The solute rolls into the spaces between the solvent. In between, first step. After this, we move to the second step, where you will have the solvent molecules we are having the solvent molecules, but now in this second step, which is the final step, the solute which are in red, solute is in red and solvent is in black. So the solute particles now attaches themselves on the solvent particles, not just being in the spaces in between, but they attach. So in the second step, as you can see, they are kind of forming a partnership between solvent particles and solute particles. Form a partnership. That partnership is now what we end up calling a solution. First step, the solute particles only roll over, being forced by the rolling particles of the solvent, roll into the spaces. They only occupy the space. Then the second step, from that space, now they attach on the solvent particles, which we shall learn much later in our science lessons, a process we call hydration. You are hydrating. That only happens if the solvent is water. If the solvent is water, then this second step is what we can call hydration. So the particles which are a solute have been hydrated by the water molecules. Hydration coming from the word hydro implying water. Enter into the spaces, attach yourself into or on the surface of the solvent particles to form a solution. So this is how we form a solution from a solute and a solvent. This comes into being by applying the kinetic theory of matter, where we are applying the rolling movement of the liquid state. The rolling movement of the liquid state to enable us have our solute into the spaces, which will later on attach themselves on the particles that are in liquid, or we can say solvent state. We also need to understand here that as some of these solutes are being put into a solvent to form a solution, we said that matter is a particle, and this particle has mass, and this particle also occupies space. So when this particle, which is a solute, enters into a solvent, it also does something else. Yes, you have already formed a solution, but this particle in between these solvent particles does something else. Being that it occupies space, it will in a way slightly push, slightly, not so much, slightly push the particles in a liquid state, the particles in the solvent, the particles in the liquid state away. Remember, they occupy space. So by occupying space, they readjust. It's like you are being forced to sit in a crowd where there is a very limited space. Even if the space is there, but it's not enough for you. So what will happen is, as you are sitting, you will still be adjusting yourself a little bit as you push your neighbors away. By doing so, you will find that some of the solutes, when being put in a solvent, they will cause overall increase in volume of the resulting solution. So if the original volume was A1, now this is the final, that is we have already added in the solute. If the original volume, that is before addition of the solute, was to this level, which we are going to call A1, the final volume will be A2. That is, we have now added in our solute. Comparing these two volumes, you will discover that this one will be slightly lower than A2. Slightly. The difference is so small that testing it in your own house or wherever you are, you might go test it and you realize maybe you are not getting that difference. The difference is so small that you require a very accurate instrument of measuring volume for you to realize it. Reason being, these solid particles only do a very little displacement of the liquid particles. But all in all, there is always an improvement on the volume of the solution. This also explains why when you are having a tea very full in your cup, let's assume you have your cup and this is the level of your tea at this point. It is not advisable you add in sugar when the tea is this full. They will always advise that have your tea in your cup 3/4 way full. Then as you add in your sugar, you will find that the volume will slightly increase. After adding in the amount of sugar you wanted, now you can fill up the tea to the level you want. Why? The answer is in the displacement of the solute particles on the liquid particles. So when you do it the first way, whereby you make sure that your tea is full or to the level you wanted, then later on you add in sugar, when these sugar crystals comes in, which are a solute, will do some bit of displacement, whereby this tea will have to move higher. When it moves higher, it can easily go beyond the level of the cup, making it overflow, which I think you are not interested in. So this is the way to go. Reason being, the solid particles also displaces some of the liquid particles to achieve that space, resulting into a slight increase in the volume of the solution formed. Now, having seen how a solution is formed, let's look at a different state of a solution. And this state is a saturated solution. We look at a saturated solution. So this is a solution, but a solution with slightly different properties, different behaviors. So what is a saturated solution? A saturated solution is whereby in that container of yours, where you had solvent particles having so many spaces in between it, then you come and put in the solute particles to the point that there is no single space in between the solvent particles is remaining. What I'm trying to say is all the spaces in the solvent are filled up. No single one is remaining. Then at this point we say the solution you are having is a saturated solution. But we also need to remember that when we were talking about kinetic theory of matter, these particles in question, we are talking about liquids. So these particles in the liquid, which is the solvent, they can also be affected by a factor called temperature. Temperature. This factor, temperature, when you increase the temperature, you are increasing the amount of energy, kinetic energy in the particles. And as you do so, they increase in the rate at which they move. When they move so much, it means they will allow more solutes to enter. Just like, as I had given an example earlier, you have been told to sit in a crowd. The space is so small, but those seated around that space are moving in a very slow manner or are not willing to move. You will find a hard time for you to sit. Though at the end, you may sit, but you will find a hard time to move. I mean to sit. But look at a second situation whereby those seated around the space you want to sit, those small, are a bit more mobile, moving so much. You will find it easier and faster for you to sit. So, why are they moving so much? Because they have more energy. First state, why were they moving so slowly? Maybe because they don't have enough energy. The same scenario can be seen here. When you increase temperature, you make the particles to be more mobile because they have the energy. And by being more mobile, they easily accommodate any new coming in particle, which is now for our state a solute. So, when you are talking about a saturated solution, you have to put in mind temperature. At what temperature are you talking about? So, by defining a saturated solution, we say a saturated solution is that solution where no more solute solute, which is our solid. No more solute, which is our solid, can be accommodated, can be dissolved in the solvent, which is our liquid. No more solute, which is our solid, can be dissolved or accommodated in that solvent, which is our liquid. Now we have added in something else at that particular temperature. And temperature here we are talking about just heat, because heat energy and temperature are one and the same. More heat means high temperature. Less heat means less temperature. So when defining solubility, a saturated solution, you have to look at the solubility of the solute in the solvent at a particular temperature. Solubility of the solute in a particular solvent at a particular temperature. Why a particular temperature? Because variation in temperature will always vary solubility of a solute in a solvent to give us a solution. Furthermore, in addition to what you have just looked at in relation to this, we have to understand other things that happen, other behaviors exhibited by a solution when different conditions are applied to the same solution. You have a saturated solution, but you apply different conditions to it. What happens? So this one is going to be looked at in terms of questions I will be posing, or conditions or observations that I will be posing. Then we try to explain those conditions as affecting the solution. The solution can be either as a saturated solution or a plain solution, but those solutions will always behave differently under different conditions. The first condition is when a saturated solution of copper 2 sulphate is filtered, some blue copper sulphate is got in the filter paper. Here you are having a solution, not now a saturated solution, but you are having a solution. And this solution is copper 2 sulphate. Copper 2 sulphate solution. So this solution, as the statement goes, that this solution of copper 2 sulphate means it was formed when we added copper 2 sulphate crystals. Remember this a solution. We added copper 2 sulphate crystals into water as a solvent. The copper 2 sulphate crystals rearranged themselves in the spaces created by the water, which is the solvent, until it formed a solution. But we have gone further again in the statement. We are now not just talking about a saturated, a solution of copper 2 sulphate, but we are now talking about a saturated copper 2 sulphate solution. So the question or the statement is, when a saturated solution of copper 2 sulphate is filtered, some blue copper sulphate is got in the filter paper. Blue solid, blue crystals, that is, it is in solid. But we have said it is a solid that has already been put into a liquid, which is our solvent, to give us a solution. To give us a solution. It is already a solution. But this solution is no longer just not a solution, since all the spaces in the liquid were filled up, which is water, by the solid, which is copper 2 sulphate crystals, we formed a solution which is saturated. Now this saturated solution we want to filter. You have your filter funnel. Into it you have fitted in a filter paper. You have a container that will be holding your filtrate. Then on pouring in the filter funnel, on pouring in the solution which is now saturated, no more copper sulphate can be dissolved in the water. So saturated solution of copper to sulphate solution. What you get is a filtrate. But the statement is telling us that some solids of copper sulphate is found or is seen on the filter paper, which are blue in color. So at the end of it all, this solid, much of it will reduce, but we shall still have some solids remaining. As you can see, now we have some solids remaining. Why? The answer lies in temperature. Remember when we talked about a saturated solution, we said as much as we'll be talking about how much solute is dissolving in that solvent, but it must be at a particular temperature, which is a factor that affects the rate at which a solid will dissolve in a solvent. So when filtering this saturated solution, you expose the solution. You expose this solution, you are filtering to the environment, which is a little bit more cold. Than it was. So by so doing, you lower the temperature at which this solution had been prepared. Maybe the solution was prepared at 25 degrees centigrade. But on pouring on this filter paper, which is cold, in this filter funnel, which is cold, the temperature of the solution, which is saturated, was lowered. Let's assume it has been lowered. Now the temperature at this point is at 23.5 degrees centigrade. Even if the drop is this small, it is a drop. And at the end, it will automatically affect the rate at which the solid, which is copper 2 sulphate, crystals dissolve in the liquid, which is water for our case here. When this happens, the particles that had easily been accommodated between the liquid particles are now forced, because the liquid particles now come together. The temperature, the energy they had previously moving around so that they can accommodate the solute is no longer there. So they come back. When coming back, they find the solid particle is there. But since that is their space, for them they can move. The solid is not supposed to move. It only moves based on the liquid, so that it can roll over the liquid to enter the spaces. It is pushed out. Assume a case of there are 4 seats, 5 people seated on the seat. And why 5? Because these other 4 were accommodating the 5th one. In a classroom where maybe the teacher is not there, the students are seated, 5 of them on 4 seats, which are packed close by. Then the teacher just enters and says, each one of you sit on your own seat. These 4 will want to go back to their own seat. This one then must be pushed out. Being pushed out means the saturation level, the accommodation level of fossils must just be 4. At that point, it was 5. But at the moment, it is 4. So being 4, the 5th one must be pushed out. It's the same case here. This is a situation whereby you are accommodating more. But on reducing the temperature, the level of accommodation is reduced. Having been reduced, the excess must be pushed out, and is pushed out as a solid because it was a solid. So it goes out as a solid. This is what we call crystallization. The process of a solid that was once in a solution, in a saturated solution, being pushed out because of reduction in temperature is what we call crystallization. So the copper 2 sulfate crystals were crystallized out because of reduction in temperature. And being blue in color, that's why whatever remained on top was to be blue in color. So let's assume the red one is blue in color. So this one is blue in color, which is copper 2 sulfate crystals, having been crystallized out. Reason? Reduced temperature. Why? The filter paper and the filter funnel were more cold than the solution prepared. Now that is one of the behaviors a solution will show when exposed to different conditions, and the condition here being a saturated solution having been exposed to a cold condition. Let's look at the second condition. The second condition here is when a saturated solution of copper 2 sulfate is heated, some more copper sulfate crystals can be dissolved in it. Now that's the opposite. We still have our solid copper 2 sulfate crystals being put in a liquid, which is our solvent, water, to give us our solution. Sorry. And this solution is a saturated solution. But now we are exposing it to a different condition, and the condition here is heat. So this solution of ours is saturated, and now we are doing heating. When you heat, as I said earlier, heat is energy, and this energy in those particles, it makes them to be more mobile, more vigorous in movement. And when they are more vigorous, they are more accommodating. As I gave an example of people seated around a space, but they are still. And another set where the same people are seated around a space, but they are mobile. You will realize that those that are mobile can easily and faster accommodate another one without much hassle. So the same is applied here. When you have a saturated solution, having these solid and liquid particles together, and you add in more heat energy, you make these liquid particles to be more mobile. And as they are more mobile, they create more spaces. More mobile makes them to have more spaces, or create more spaces. By creating those more spaces, then they give room to more solid, which is our copper 2 sulfate crystals, to be added in. Using a model, we had our liquid particles which had already formed a solution. And a solution here we said that they get attached. So the solid particles are attached on the liquid particles. But remember, being a saturated solution, all the spaces must be filled. All the spaces have been filled. So we have no space. All the spaces are filled. This is a saturated solution. When you do heating, you make the liquid particles, the ones in black, to be more mobile. When they are more mobile, it means they create more spaces between them. The particles move slightly far away from each other. As you can see, these ones are a bit more close than these ones. But still, they are having the previous particles they had attached to them. But now, though they are attached to them, we can see some spaces in it. Because of this, you can now be able to add more solute. So the point here is when you do heating of a saturated solution, you make the solvent or the liquid particles to be more mobile. When they become more mobile, they create more spaces between them. And when they create the more spaces, more solute can be added until that point where all the spaces will have been filled, and then you say you have again acquired a new saturated solution. If this was at 25 degrees centigrade, you heated this solution to 50 degrees centigrade, then the amount of solute you added in 25 to achieve a saturated solution will be less than the amount of solute you will have added in 50 to form a saturated solution. It doesn't mean that if this is a half of this, then the solute must be a half. No, it varies. It will depend on the type of solute. All these solutes or all these solids do not have the same size of particles. So you'll find that those solutes or those solids that have much smaller sized particles, much of it will be added. But those that are bigger in size, very little amount of the solid will be added. Maybe to give an account of what I've just said on big and small particles, you can have in your cup or any container marbles. Let's start with the pool balls. If you have pool balls in a container, they are big in size. Then you have another case where you have marbles which are smaller in size. You take marbles as a comparative size to the pool-based balls. Then you get any circular, like the ball bearings of maybe a bicycle, a vehicle, any, but smaller in size. Then you pour them here and in this one. You will discover that this will not occupy the same amount of those small bearings to this. This one has smaller spaces, this one has bigger spaces remaining. Now, let's take these two solids as pool balls and marbles as our two solutes that we want to add in a solvent, these two. And our solvent is a packet or a basin having pool balls. So these ones are the same as this, but we are assuming this one is a liquid and this one is a solid. These particles are for water. These are particles of one solid A and these are particles of solid B. You will discover that very few in number of these ones will be added in this. You can try it at home. And so many of these will be added in these and without realizing that even some of these have been added here. Reason being, these ones being small will be accommodated in the spaces. So it's only at that point whereby all the spaces will be filled up that now you will notice the volume of this one increasing. But for this one, you add in, then you will find that the volume is increasing. The magic in the movement or in the increase of the volume is in the size. So not all solids behave in the same way when put in a liquid or a solvent to form a solution. So as you have seen here, increase in heat increases movement of particles in liquid, making them create more spaces that allow addition of more of the solute. Another condition is when a saturated solution of copper 2 sulphate is first filtered and then cooled, blue crystals of copper sulphate form on the bottom of the container. When a saturated solution you have filtered, then cooled. This third condition is similar to what we looked at in the first state, where we said you are pouring saturated solution on a filter paper which is in a filter funnel to filter, to get that filtrate of copper 2 sulphate. On the surface of the filter paper, we saw crystals of blue copper 2 sulphate. Here we are being told you filter a saturated solution of copper 2 sulphate. On filtering, you poured here your copper 2 sulphate. On filtering, you have gotten your filtrate. But remember, this one is saturated. So we are talking about a solution, but a solution that is saturated. On cooling this solution that has been filtered, what we call a filtrate, you discover that there are some solids, crystals, that are formed at the bottom of the container. As the statement reads, when saturated solution of copper sulphate is first filtered and then cooled, blue crystals of copper sulphate form on the bottom of the container, as you can see it here. So these are solids, blue crystals of copper 2 sulphate being formed on the bottom of the container. Why? We have just mentioned the word cooled. Cooled. What is cooling? Cooling is withdrawal of heat energy on a substance. And when you withdraw heat energy from a substance, you make its particles to be less mobile. They reduce on their mobility. And by reducing on their mobility, they reduce on the creation of space. And by reducing on the creation of space, they push out any that had come in to take the space they had created earlier when they were hot. Because when hot, they were more mobile. And when more mobile, they were creating space. On creating the space, a solute was introduced, which took that space. But here, you are doing a cooling process. On cooling, the energy that liquid particle had that was making it move so much has been withdrawn. So it makes the particle to be less mobile. On so doing, it comes to occupy the previous space it occupied when it had less energy, which is at the moment being occupied by a solid, which is copper to sulphate. As a result, this solid must be displaced, must be pushed out. It's like you had just been welcomed, now it is your time to leave. When leaving, when being pushed out, is what we call being crystallized out, as I had mentioned earlier. So, the solids that are being formed here are crystals of copper to sulphate, which have been formed in a process called crystallization. A process called crystallization, which is the process of forming a solid from a saturated solution when the temperature of the solution has been lowered, as we have done it. The fourth condition is when a saturated solution of copper to sulphate is made, no more copper sulphate will dissolve at that temperature. No more copper sulphate will dissolve at that temperature. However, when some sodium chloride crystals are added, they do dissolve. This is a very good condition that some may easily get confused. Why? You are adding this one, it can't dissolve. But you add in this one and it dissolves. This is a similar case like what I've just used to explain using the pool balls and the marbles. When you have a saturated solution being taken as our pool balls, meaning that this solution has been made by dissolving a solid called the pool balls. Pool balls, they are big in size, or golf balls. They are big in size. So, and you don't want to go beyond this level. You can't go beyond this level. You will discover that there is no way I can add in this other pool or golf ball into this. So it's the same as this. When a saturated solution of copper sulphate is made, no more copper sulphate will dissolve at that temperature. So we are not varying the vibration, the movement levels of this liquid. There is no addition, there is no subtraction. The temperature is constant. We can't add any extra ball of pool or any extra ball of golf. But we have been told if you introduce another solid by the name sodium chloride crystals, sodium chloride crystal, it is a solid just like this. It is a solid just like copper sulphate. Here, let's now introduce a marble ball. So we introduce a marble ball. It's smaller in size. So this one is taking the position of copper sulphate, and this one is taking the position of sodium chloride. The answer to this question is in size. Size is our answer. Size is our answer. This one being larger in size, copper sulfate being larger in size, cannot fit in the smaller spaces remaining in that saturated solution. So what does it tell us? Even if in a saturated solution we have said that all the spaces have been filled, but they have been filled for that particle of that particular size. For that particle of that particular size. All the spaces here have been filled, but for that particle of that particular size. But for a particle that is smaller, there is a lot of room. And that is what the sodium chloride use. So the sodium chloride particles will come and comfortably fit in the small spaces that were remaining, that cannot be able to accommodate the copper sulfate. The marbles will come in and occupy the spaces that had been left in the saturated solution that cannot be able to fit the copper sulfate, which is being represented here by a golf ball, which is bigger in size. So the answer is in size. This tells us that a saturated solution is that solution that cannot allow any more solute of the same. So there's now an addition. More solute of the same substance to a solvent at a particular temperature. So we have done some improvement on our definition. Previously we had said a solute being dissolved in a solvent at a particular temperature. No more solute can be dissolved in that solvent at that particular temperature. But now we are modifying by advancing our definition by saying that a saturated solution is that solution formed from a solvent not accommodating any more solute of a particular substance. So the addition is particular substance at a particular temperature, as you have seen it here. This is particular. It can't accommodate anymore, but this one is not particular. These are different solid, and that's why it can easily be accommodated. Reason, size. It is smaller and is bigger in size. The other condition is while the boiling point of pure water is 100 degrees centigrade, and remember this is at sea level, not all points will get 100 degrees centigrade as boiling point for water. When you go high, probably on a mountain or any other point that is high, you will realize that water will boil at a temperature less than 100 degrees centigrade. Reason being, pressure will have reduced. The higher you go, the less the pressure. And when you reduce on the pressure that is pushing on the water, then it boils at a lower temperature. And when you go to a point that is lesser in level than the sea level, then water will boil at a higher temperature than 100 degrees centigrade. Reason being, again, pressure, but at that point the pressure is high. So due to the high pressure, then the water will boil at a higher temperature. So here we are being told that while the boiling point of pure water is 100 degrees centigrade, it is observed that the boiling point of saturated copper sulfate solution is 104 degrees centigrade. So, assuming that we are at sea level, assuming that we are at sea level, where we have been told that at this sea level, when you are heating this water of yours, it boils at 100 degrees centigrade. At the same sea level, same container, same conditions, you now introduce copper sulfate crystals in it to form a saturated solution or just a solution. Here it doesn't matter whether it is a saturated solution or a solution. In the question we are being told that pure water in relation to saturated copper sulfate. They are relating to saturated copper sulfate, but it can either be saturated or not, so long as it is a solution. So you introduce, we introduce our copper sulfate crystals. This is a solution. Going by the question, it is saturated, but the effect on the explanation will both apply for saturated and unsaturated solution. Now, when heating this water, which was pure, it is boiled at 100 degrees centigrade. But here you are now boiling water that is not pure. It is impure. A solution contains a solute, and a solute is a foreign particle in that solvent. If your interest was to have that solvent alone, then introduction of a solute makes it to be an impurity. It is a foreign particle. So the presence of the foreign particle in the solvent will also play a role on how the water molecules will be affected by the heat energy. These particles will also absorb some heat energy, and when they absorb those that heat energy, it means you will require more for all the water molecules to get the heat energy as they were supposed to get. Remember, for boiling to take place, all the water molecules must get enough energy to push them to 100 degrees centigrade. But here is a case whereby some of the energy is kind of being snatched away. It is being stolen. It is being stolen. But you have to make sure that you reach there. And if you are to reach there, then you have to add in excess. And the excess here is now what makes it to move from 100 to 104 degrees centigrade. Now, why these 4? These 4 degrees centigrade is because of the extra energy, extra heat energy that was put in so that it can cater for the copper sulfate crystals. The water, it is just 100. But there is something in it, which is copper sulfate, which must also be worked on. So, being that it has to be worked on, more energy has to be put in so that it can also be accommodated in the heating. So by doing so, you find that in general, you have to have the energy for the water and the energy of the particle, which is foreign, put together to give us now the overall temperature at which the whole solution will have to boil, and which is 104 degrees centigrade. Then what does this one tell us? This tells us that in case you encounter boiling water or encounter boiling solution, for you to be very careful on which solution to handle in which way, look at the density of that liquid or that solution or that solvent. The more dense it is and it is boiling, the more dangerous it is, because it will be at a higher temperature than the lighter one. Looking at a case of, for example, ethanol. Ethanol is lighter than water. This makes it to boil at a lower temperature. Look at tea. Tea has sugar in it. It can have tea leaves, or it can have coffee. It can have whichever beverage you are using. that is a solid. Again, look at it in terms of that coffee you have prepared, but minus tea, and it is boiling. Then look at it again as water with the sugar, but minus that beverage. All those solutions will have different temperatures because the amount of solids in that water is varying. So the more the solids, the higher the temperature at which the solution will be. The other condition is when enough copper sulfate is added to exactly 100 mils of water. So we want to form a solution here. So we are being told when enough copper sulfate is added to exactly 100 mils. So if you can take this container, we want to prepare a solution. We have water, and this water is 100 mils of water to form a saturated solution. The final volume is 103 mils. 103 mils. So we have case 1, plain water, 100 mils. Case 2, now the solution is being formed. This is 100, but we are being told this one goes to 103 mils. 103 mils. Why? As I was beginning the lesson, looking at how a solution is formed, I mentioned something to do with a solid and a solvent must come together to form a solution. And in coming together, we have 2 steps. Step number 1 is the solid particles, and in our case here, the solid particles are copper sulfate, roll because of the liquid being able to move, to roll over each other. As they are rolling over each other, they make these solids also to move. Not that solid particles move, they only vibrate. But because they are on a surface that is slippery, it is rolling, they also move. And they move to enter into spaces that have been left by the solvent, in our case being water, which is 100 mils. The second step was those solids now get attached on the liquid particles, which is our water molecules, get attached on the water molecules. A process we normally call hydration, where now the particles are being hydrated. They are being attached on the surface of the water molecules. That is, they have now formed a solution. But now remember, as we are forming this solution, we moved from a solution now to a saturated solution, where we said a saturated solution is whereby you add in as much solute as possible in that solvent until no more space is left. But we have just clarified a point here. Until no more space is left for that particular substance, not any other, for that particular substance. So in that case, no space is left. But as the solids are being attached on the surface in that space, there were situations whereby you had to readjust yourself as a liquid so that these solids fits very well, this solid fits very well, this solid fits very well, until no space is totally left. In so doing, as you are readjusting yourself as a liquid, you may easily take up some space. Just like the 5 students on the 4 chairs. You will find that some may easily sit away from the chair, just a little bit. Even if it is 1 centimeter, it is away from the chair. So that 1 centimeter is because of the extra person you accommodated. So it is because of the solids you put in. And because of that displacement, that pushing, that movement of the liquid molecules, the water molecules, is what made now the volume to increase to 103. And this is why I said when you are adding in sugar in your tea, please take 3/4 of the volume, add in the crystals of sugar. After that is when you fill up the cup. Reason, you don't know how much will be displaced in terms of volume. For this case, it has been done experimentally and discovered that an extra of 3 mils will be done. And the extra is because of the movement of the liquid particles to accommodate the solid particles. The last condition is if a saturated solution is filtered and then the filtrate heated to evaporate some water, solute crystals form on the bottom of the container. So these are cases where you have a solution. This is a saturated solution, and this saturated solution you have filtered, you are sure what you are having is your saturated solution, very sure. Then you subject it to heat. Heat obviously makes the particles in a liquid state to gain more energy. And in case they gain excess energy, they will vibrate excessively until they break off. So when you are heating these water molecules, which were just rolling over each other because of the little amount of energy they have, they are now gaining more energy until the vibration is so much, the movement is so much that now the particles, some of the particles starts breaking off. They break off as steam. When they break off as steam. This process will continue until all the water in the solution has been evaporated. At that point, the copper sulphate, which was a solute, will now not be in attachment with the liquid particles, which was water. It will have remained on its own. So it will be seen as a solid at the bottom of the container, but not in attachment with the previous partner, which was the water molecules, which together they formed a saturated solution. So an overview of what we have just been seeing in these all conditions are that in the kinetic theory of matter, we are always looking at movement of particles. But in this movement of particles, different behaviors, different properties are seen in relation to those substances that are either in solid, in liquid, and in a gaseous state. And these conditions can also be seen because of the variation on the conditions applied in those states, which leads to all the explanations we have done. I hope now at the moment we can be able to explain as many aspects we encounter in our daily lives as possible. That's the end of our lesson today. Thank you.